We are going to study Noether's theorem, a topic you cannot miss in one of the early chapters of your textbook on quantum field theory. Noether's theorem is known to be one of the most profound discoveries in theoretical physics. You can summarize it in a single sentence. Each continuous symmetry of a physical system implies the existence of a conserved quantity. The familiar conservation laws you learned in school, such as the conservation of energy, linear momentum, angular momentum, are all inevitable consequences of the underlying symmetries. Quantum field theory is not the first place you encounter Noether's theorem. If you have taken a course on advanced classical mechanics, you probably have studied Noether's theorem there. For a point particle, there is a simple intuitive way to illustrate the idea. In Lagrangian mechanics, imagine a particle trajectory satisfying the equation of motion that is derived from the principle of least action. Call the two endpoints of the trajectory A and B. Apply a symmetry transformation to path AB and call the new trajectory path CD. By definition, the two paths give the same value when we compute the action functional over them. Assume that the two paths are very close to each other. Draw a short line segment from A to C and another one from B to D. Compare the detour route that goes from A to C to D to B and the direct route from A to B. The principle of least action tells us that the difference in the value of the action functional vanishes to the linear order in the infinitesimal parameter for the displacement. If we recall that path CD and path AB give exactly the same value of the action functional, we conclude that the action functional evaluated over the AC interval should be equal to that over the PD interval. If some quantity maintains the same value between the initial stage and the final stage of motion, we may as well call it a conserved quantity. The Noether's theorem appearing in an early chapter of a QFT textbook is a part of classical field theory. Quantum mechanics doesn't play any role yet. What is the main difference between the particle mechanics and the continuum mechanics of a field? Yes, the field is spread over a large area of space. So, we cannot simply choose an initial point and a final point over the time axis. Rather, we should choose a region in space-time with some boundary condition for the field. And then we examine how the field inside the region and the region itself are transformed by symmetry. When you study electromagnetism, you must have seen how charge conservation is related to current conservation and vice versa. Noether's theorem applied to a point particle gives an equation that looks mathematically identical to charge conservation. Similarly, Noether's theorem applied to a field theory gives an equation that looks like current conservation. Since we are studying relativistic QFT, we should also remember to express the current conservation in a Lorentz covariant notation. Symmetry in physics is largely divided into discrete ones and continuous ones. Noether's theorem only addresses the continuous ones. Continuous symmetries are in turn split into two categories: space-time symmetry that maps space-time points to one another, and internal symmetry that transforms the field independently at each point of space-time. If we take a deep dive into the space-time symmetry, we also run into something called supersymmetry, but we will not discuss supersymmetry in this lecture. Let's take a closer look at internal symmetry first. As far as the proof of the Noether's theorem goes, internal symmetry is a lot easier than space-time symmetry. In general, symmetry means invariance under a transformation. A defining feature of internal symmetry is that the fields at different space-time points never get mixed up by the transformation. The value of the field at a space-time point after the transformation depends only on the value of the field at the same point. Internal symmetry also forbids derivatives of the field, because derivatives necessarily compare the values of the field at nearby points. Perhaps the simplest example of an internal symmetry is the phase rotation of a complex scalar field. To cook up a slightly more complicated example, we can introduce a set of scalar fields that act like components of a vector in some internal space, and consider a linear transformation acting on that vector space. As we saw in the particle mechanics setting, Noether's theorem always consists of two assumptions and one conclusion. Assumption number one is symmetry. For internal symmetry, we require that the Lagrangian density remains unchanged. Assumption number two is equation of motion. As always, the equation of motion is given in the Euler-Lagrange form. The conclusion is an explicit formula for a conserved current derived from the internal symmetry. The construction of the conserved current for internal symmetry is simple enough. The symmetry assumption implies that the difference of the Lagrangian should vanish. In general, when two slightly different field configurations are given, the infinitesimal change of the Lagrangian can be expanded as shown in the second line. As we move to the third line, we move the derivatives around as we often do for integration by parts. The last group of terms vanish by the equation of motion. The surviving term gives the conserved current we were searching for. Here is a simple but important example. Consider a complex scalar field. Assume that the Lagrangian contains the standard kinetic term and a potential term that depends only on the magnitude of the scalar field. The symmetry in question is the phase rotation of a complex variable. Infinitesimally, the transformation gives what is written in the second line. It is straightforward to derive the conserved current. The final result is at the bottom of this page. Even if you don't fully understand the derivation, you can easily verify that the equation of motion implies the current conservation. After having studied internal symmetry as a warm-up exercise, we can move on to space-time symmetry. I have to warn you that space-time symmetry turns out to be substantially more complicated than internal symmetry. Quite literally, space-time transformations map the space-time points to one another. If we start from a point in space-time and follow the consequences of a continuous transformation, we will obtain a curve. For example, a translation will give us a straight line, and a rotation will give us a circle. A continuous transformation can always be understood as an integration of infinitesimal transformations. The direction of the infinitesimal transformation can be expressed as a tangent vector to the curves we just saw. I hope you recognize the relation between the curves and their tangent vectors in the two figures shown here. From here on, we will use the symbol capital K to denote this spacetime vector associated with an infinitesimal transformation. In a relativistic four-vector notation, we may write the infinitesimal change of the spacetime coordinate as delta x equals epsilon times k. In the relativistic theory, the translation in space and time together give four independent transformations, and the rotations and Lorentz boosts together give 6 transformations. We may borrow a common notation from a quantum mechanics textbook and denote the translation by P and the rotation and Lorentz boost by L. The vector index for the K vector and the vector indices to label the types of transformation look mixed up, which may cause some confusion for beginners. But eventually, you can convince yourself that for the 10 space-time transformations, what I wrote in the middle of this slide makes perfect sense. Each of the 10 K vectors satisfies a simple equation at the bottom. We'll use this equation later in the lecture. I recommend you to check this equation for the 10 K vectors listed here. I told you earlier that spacetime symmetry is more difficult than internal symmetry. The main reason for the difficulty is that spacetime symmetry acts on different fields in different ways. You may have heard of types of fields, such as scalar, vector, tensor, or spinor. Those names are there to distinguish how the field responds to the spacetime transformation. In this lecture, we do not plan to cover all possible types of fields. We will focus on just two types, scalar and vector. When we apply translation and Lorentz transformation to space-time points, a scalar field carries its value from one point to another. The new field configuration evaluated at the new spacetime point has the same value as the old field configuration at the original spacetime point. How does a vector transform? The short answer is that it does not behave like a scalar field. We will see more details later. So much for the introduction to spacetime symmetry. Let's proceed to compute the conserved currents for spacetime symmetry acting on a scalar field. When we are dealing with internal symmetry, the value of the field changed at a fixed point in spacetime. When it comes to spacetime symmetry, the spacetime points move around and the value of the field changes accordingly. Scalar fields are the easiest in that the new field at the new point should be the same as the old field at the original point. In equations, we denote the new field by phi prime. If we define the infinitesimal change delta phi as the difference between phi prime at x prime minus phi at x, then delta phi is identically zero by construction. Something that vanishes all the time is not too useful, so we choose to split this zero into two pieces. If we subtract phi prime at x once and then add the same thing, we can approximate the first group of terms as a directional derivative. The second group is the difference between two field configurations at the same point. We call this difference delta bar phi to distinguish it from the delta phi above. The new displacement delta bar phi is somewhat similar to the displacement for an internal symmetry. The fact that the original delta phi is identically zero implies that the delta bar phi is determined by a directional derivative acting on phi. For internal symmetries, the displacement of phi and the displacement of the gradient phi were related in a simple manner. That is not the case for spacetime symmetries. The reason is that the spacetime points that enter the definition of the derivatives get transformed. All we need is the chain rule for derivatives. If we compare partial mu acting on phi to partial prime mu acting on phi prime, and keep only the linear terms in infinitesimal displacement, then we get a simple expressions in the lower right corner. With the careful preparation of the displacements, we are ready to run the Noether procedure. As usual, we demand that the action functional takes the same value before and after the transformation. A new feature of the spacetime symmetry is that the integral measure is affected by the transformation. So the variation of the action has two contributions, one from the integral measure, the other from the Lagrangian. Let's look at the integral measure first. In general, when we connect two coordinate systems, the integral measure gets multiplied by the determinant of the Jacobian matrix. When the coordinate transformation is infinitesimal, the Jacobian matrix is slightly away from the identity matrix. Then we can use the formula relating the determinant to the trace. The end result is the divergence of the vector representing the displacement of the coordinates. We plug this divergence into the action functional. Then we use the product rule for derivatives to rewrite the term as the sum of a total derivative and a directional derivative acting on the Lagrangian. Since the Lagrangian is a function of the field phi and its partial derivatives, we can use the chain rule to expand the term. In the last step, we rewrite a term using the delta bar phi we defined earlier. Next, we turn to the variation of the Lagrangian. We assume that the Lagrangian consists of the standard kinetic term and a potential term that depends on phi. Since delta phi vanishes, the variation of the potential vanishes, and we may focus on the variation of the kinetic term. Again, we use the product rule for derivatives to reshuffle the terms and express the results in terms of the delta bar phi whenever applicable. It is time to collect everything and reach a conclusion. Both the integral measure and the Lagrangian produce three terms. We write the contributions in a parallel way to make it easy to see how they conspire to give the desired answer. The last terms in the two lines cancel each other. The terms in the middle vanish by the equation of motion. Finally, the leftmost terms in the light blue box is a total derivatives signaling a conservation law. No matter how complicated the intermediate steps are, the conclusion of the Noether procedure is the conservation law. The variation of the action contains a term proportional to the equation of motion and the four-dimensional divergence of the conserved current. For a scalar field, the explicit form of the current can be summarized in a single line as shown here. When the conserved charge of a point particle is a scalar quantity, the corresponding conserved current for a field is a vector quantity. Energy and momentum, which are charges for the space-time translation symmetries, form a vector in the sense of four-dimensional special relativity. So if we move from a point particle to a field, the corresponding current will become something more complicated than a vector. The thing is called the energy-momentum tensor. How do we obtain the energy-momentum tensor for a scalar field? The general Noether current we computed before is available in the upper right corner. If we express the space-time displacement and the field displacement in terms of the k vector for the symmetry transformation, we obtain the conserved current J that depends on k. A short computation shows that J is always a tensor T partially contracted with the k vector. This T is precisely the energy-momentum tensor we were looking for. For the familiar Klein-Gordon Lagrangian, the explicit form of the energy-momentum tensor is as shown here. The derivation of the energy-momentum tensor given in this video may look different from the ones you saw in your favorite textbook, but the final result must agree. Our next topic is the space-time symmetry of a vector field. We may imagine many different vector fields, but we will focus on the most famous one, the Maxwell field from electromagnetism. Our goal is to derive the energy-momentum tensor of the Maxwell field. At this point, some QFT textbooks provide a rather dubious explanation on this topic. They write down the formula for the conserved currents for the scalar field as we derived earlier today, and then simply replace the scalar phi by the vector A nu. Can we hope to get lucky enough to obtain a correct answer that way? If a student studying Noether's theorem for the first time makes such an attempt, we may say, nice try, but tough luck. But if professors keep presenting such a half-baked idea, the students will have to suffer for no good reason. Let me say it out loud. Replacing the scalar field by the vector field with no additional action is simply wrong. I wondered for some time why any serious theorist would continue to spread the wrong derivation. My best guess is that they landed on a sort of a compromise. A fully rigorous description of the space-time transformation requires a working knowledge of differential geometry, roughly at a level covered by an introductory course on general relativity. In reality, many students taking their first course in QFT lack experience in differential geometry. So, the instructors of QFT may be tempted to cheat a little bit and use a wrong derivation that looks easy for a beginner. The good news is that you don't have to suffer anymore. The derivation I'm presenting in this video is elementary and rigorous at the same time. The first thing to note is that the transformation of the vector field receives contribution from the Jacobian matrix. As far as the transformation property is concerned, the variation of A mu is essentially the same as the variation of partial mu phi we computed before. Applying the same method to the field strength tensor F mu nu, we obtain a slightly more complicated expression for the variation delta F mu nu. We are not bothering to define something like the delta bar phi we introduced for the scalar field. As a consequence, the delta F mu nu here does not contain any derivative acting on F. We are ready to run the Noether procedure. As before, we have two main contributions, one from the integral measure, the other from the Lagrangian. Compared to the scalar case, the computations are slightly more complicated, but the strategy is exactly the same. After the dust settles, we obtain three terms. The first term is the conserved quantity we were searching for. The second term is the equation of motion. The last term exhibits the difference between the vector field and the scalar field. It vanishes due to the so-called Bianchi identity, which holds automatically as long as F mu nu is derived from the vector field A mu in the standard way. It has been a long journey, but we have succeeded in deriving the energy momentum tensor of the Maxwell field in a rigorous but elementary way. This energy momentum tensor agrees with the energy density and the pointing vector you encountered in your textbooks on electromagnetism. The energy momentum tensor of the Maxwell field naturally leads us to the final topic of this lecture, something called conformal symmetry. The translation and rotation symmetries we studied earlier preserve not only the lengths of the vectors, but also the angles between different vectors. Conformal symmetry means that we give up the length and require only that the angles be preserved. In special relativity, we measure the distances and angles using the metric tensor. So if the metric tensor after the transformation is a scalar function times the original metric, the transformation defines a conformal symmetry. In terms of the Jacobian matrix produced by any coordinate transformation, the ratio between the two metric tensors is equal to the square root of the determinant of the Jacobian. Looking into the infinitesimal transformation, we can write down a differential equation for the vector field K, which is called the conformal Killing equation. Here, Killing is the name of a mathematician. In 4 spacetime dimensions, there are only a handful of independent solutions to the conformal Killing equation. In addition to the well-known translations and rotations, we have two new members. The symbol D refers to dilatation. It can zoom in or zoom out the whole spacetime in a uniform way. The other one, labeled K sub rho, looks more complicated. It is called special conformal transformation. The dilatation is easy to visualize. The special conformal transformation is hard to visualize. It may be a good idea to draw some pictures using computers and try to gain some intuition. Coming back to physics, the hidden symmetry of the Maxwell theory is that the action is invariant under all conformal transformations. We could take infinitesimal variations as before, but let me show you instead how to verify the invariance under a finite transformation. The integral measure acquires the determinant of the Jacobian matrix in the standard manner. The field strength tensor F mu nu gets multiplied by the Jacobian and is transposed. The conclusion is that the determinant of the Jacobian factors cancel out completely and leave the action invariant. The conserved currents for the conformal transformations are again given by the product of the energy momentum tensor and the k vector. Now the list of k vectors includes dilatation and special conformal transformation. The conservation laws and the conformal killing equation together imply that the trace of the energy momentum tensor must vanish. It is a general fact that must be true for any conformally invariant field theory. For the Maxwell field, even if you know nothing about conformal symmetry, you can easily show that the trace vanishes. Today's lecture had only one main theme, Noether's theorem, but the exposition was somewhat lengthy. Let me recap what we covered. We started off by explaining the key idea behind Noether's theorem in the context of a point-particle mechanics. Turning to QFT, we chose to discuss internal symmetry and space-time symmetry separately. Space-time symmetry takes more effort, but we successfully derived the energy momentum tensor for scalar and vector fields. In doing so, we corrected a widespread error regarding the derivation for the vector field. Finally, we demonstrated the less obvious conformal symmetry of the Maxwell action. Of course, symmetries and conservation laws are of utmost importance throughout your study of QFT. I hope you'll learn them by heart.